The speed of light traveling through a vacuum is almost 1 billion feet per second, equivalent to about 190,000 miles per second. This incredible speed is a universal constant known as c, or light speed, which is prominently featured in equations. According to the physicist Albert Einstein's theory of special relativity, which forms the basis of much of modern physics, nothing in the universe can travel faster than light. As matter approaches the speed of light, its mass becomes infinite, serving as a speed limit for the entire universe. The speed of light is so immutable that it is used to define the international standards measurements such as meter, mile, foot, and the inch, as stated by the United States National Institute of the Standards and Technology. Additionally, it plays a role in defining other fundamental units like the kilogram and the temperature unit Kelvin through intricate equations. Despite the speed of light's reputation as a universal constant, scientists and science fiction writers continue to contemplate the possibility of faster-than-light travel. While no one has been able to demonstrate a real warp drive through this far, this hasn't deterred our collective pursuit of new stories, inventions, and the realm of physics. One common unit of measurement in astronomy and physics is the light year, which represents the distance that light can travel in 1 year, equivalent to about 6 trillion miles. It provides a way for astronomers and physicists to measure vast distances across our universe. For instance, light from the moon takes about 1 second to reach our eyes, making the moon approximately 1 light second away. Sunlight, on the other hand, takes about 8 minutes to reach us, placing the sun at a distance of approximately 8 light minutes. Even the nearest star system to our own, Alpha Centauri, requires roughly 4.3 years for its light to reach us, making it 4.3 light years away. When astronomers observe objects beyond our solar system, they often encounter distances ranging from a few light years to billions of light years. Interestingly, everything they see in the distant universe is actually a glimpse into the past. The light they observe left those objects a long time ago, so by studying it, they're essentially looking back in time. This principle allows astronomers to observe the universe as it appeared shortly after the Big Bang, which occurred approximately 13.8 billion years ago. For example, objects located 10 billion light years away appear to astronomers as they did 10 billion years ago, providing a valuable window into the early stages of the universe. The study of light and its properties has a rich history that dates back centuries. As early as 5th century, Greek philosophers such as Empedocles and Aristotle debated the nature of light speed. Empedocles proposed that light, whatever its composition, must travel and therefore have a rate of travel. In contrast, Aristotle argued in his treatise on sense and the sensible that light, unlike sound and smell, must be instantaneous. Although Aristotle's view was eventually proven wrong, it would take hundreds of years before the evidence surfaced. In the mid-1600s, the Italian astronomer Galileo conducted an experiment involving the speed of light. He positioned 2 individuals on hills less than a mile apart, each holding a shielded lantern. One person uncovered their lantern, and when the other saw the flash, they uncovered theirs as well. However, Galileo's experimental setup did not provide sufficient distance for the participant to accurately measure the speed of light. Nonetheless, he deducted that the light traveled at least 10 times faster than sound. In the 1670s, Danish astronomer Ole Romer made an important discovery while observing the moons of Jupiter. He noticed that the timing of the moon's eclipses seemed to vary depending on the Earth's position in its orbit. Romer realized that the discrepancy was due to the finite speed of light. When Earth was closer to Jupiter, the light took less time to reach us, resulting in earlier eclipses. Conversely, when Earth was further away, the light took longer, causing later eclipses. Romer's observations provided the first quantitative estimate of speed of light and solidified the notion that light takes time to travel. Another significant breakthrough came in the early 19th century when the physicist Thomas Young conducted his famous double-slit experiment. By passing light through 2 narrow slits and observing the resulting interference pattern, Young provided evidence that light behaves as a wave. This experiment demonstrated the wave-like nature of light and laid the foundation for future experiments and theories. In 1849, physicist Hippolyte Fizeau conducted an experiment to directly measure the speed of light. He directed a beam of light through a rapidly rotating cogwheel and reflected it back using a mirror placed 8 kilometers away. By adjusting the speed of rotating wheel, Fizeau managed to measure the time it took for light to travel the distance. His groundbreaking experiment produced a value close to the current accepted speed of light. Further experiments in measuring the speed of light came in the late 19th and early 20th centuries. The experiments conducted by physicists Albert Michelson and Edward Morley in 1887, known as the Michelson-Morley experiment, aimed to detect the hypothetical ether through which light was believed to propagate. However, their experiments yielded null results, indicating that there was no preferred reference frame for the speed of light and supporting Einstein's later theory of relativity. Einstein's theory of special relativity, published in 1905, revolutionized our understanding of space, time, and the speed of light. It introduced the notion that the speed of light is constant and independent of the observer's motion. This theory established the foundation for modern physics and has been extensively confirmed through numerous experiments and observations. While the speed of light is constant in a vacuum, it can be affected when light passes through various materials. When light enters a medium such as water or glass, it can slow down due to interactions with atoms and molecules in that material. The speed at which light propagates through a medium is determined by the refractive index, which measures how much the speed of light decreases relative to its speed in a vacuum. This phenomenon is responsible for optical effects like refraction, which causes a straw to appear bent when placed in a glass of water. The speed of light is serving as a fundamental constant in our universe. While it remains an unattainable speed limit for objects with mass, the study of light and its properties has led to remarkable scientific discoveries and advancement in our understanding of the universe. Through observation of light from distant objects, astronomers can peek back in time and gain insights into the early stages of the universe. The story of humanity's exploration of light speed spans centuries, with notable contributions from ancient philosophers, astronomers, and physicists, culminating in Einstein's theory of special relativity. Our ongoing quest to comprehend the nature of light continues to inspire curiosity and innovation in the realms of science and beyond. If you enjoyed this video, please consider subscribing to the channel and leaving a like.